The Gloster Meteor, Britain's first operational jet fighter, streaked across the skies of World War II, heralding the dawn of the jet age in Allied aviation, its twin engines howling the end of propeller-driven combat aircraft. A product of wartime innovation, the Meteor's distinctive twin-boom design and sleek fuselage cut a striking silhouette against the war-torn European skies. But it was more than just a pretty face. The Meteor boasted a top speed that left its piston-engined contemporaries in the dust, rocketing to over 600 miles per hour in level flight. At the time, a feat that seemed to belong more to the realm of science fiction than reality. Too afraid of its state-of-the-art technology falling into German hands, the British never gave the Meteor the chance to clash directly with the Luftwaffe's own jet-powered wonder weapon, the Me-262. Nevertheless, it carved its own legendary status by becoming the only Allied jet aircraft to see combat in World War II, proving its mettle and saving countless lives by hunting down and destroying the terrifying V-1 flying bombs that rained destruction on British cities. This versatile jet's influence extended far beyond the war years, going on to shatter world speed records, push the boundaries of high-altitude flight, and serve as a testbed for radical new technologies. From the frozen fjords of Norway to the scorching deserts of the Middle East, the Meteor's adaptability saw it operate in every corner of the globe, cementing its place as one of the most significant aircraft of the 20th century. The Gloster Meteor was a product of World War II, a conflict that accelerated technological advancement at an unprecedented pace. As the war progressed, it became clear that propeller-driven aircraft were approaching their performance limits. The quest for greater speed and altitude capabilities led to the exploration of jet propulsion, a technology that promised to revolutionize aerial warfare. In Britain, this pursuit was spearheaded by Sir Frank Whittle, whose pioneering work on jet engines laid the foundation for a new era in aviation. Whittle's first jet engine ran in 1937, but it wasn't until the early 1940s that the Air Ministry, recognizing the potential of this technology, sought to harness it in a combat aircraft. The goal was to create a fighter that could outperform the best piston-engined aircraft of the day and counter emerging threats like the V-1 flying bomb. The Gloster Aircraft Company, under the leadership of Chief Designer George Carter, was tasked with creating an airframe to utilize Whittle's innovative engines. Carter's team began work on what would become the Meteor in 1940, with the first design drawings completed in August of that year. The result was the Gloster Meteor, an aircraft that would become Britain's first operational jet fighter and the Allies' only jet aircraft to see combat during World War II. Offering a quantum leap in performance, the Meteor was designed to replace various propeller-driven fighters, such as the Spitfire and Hurricane, which had been the backbone of the RAF during the early years of the war. Born in the shadow of impending German invasion, its critical role intensified as the skies darkened with the menace of high-speed bombers and the terrifying new V-1 rocket. The context of its creation was one of urgency and innovation, with the stakes no less than the future of aerial combat. The design of the Gloster Meteor represented a significant departure from conventional fighter aircraft of the time. Its most distinctive feature was the twin-engine configuration, with the jet engines mounted in the wings rather than slung beneath them. This design choice was made for several reasons. Firstly, it allowed for a more balanced and robust airframe, crucial for an aircraft pushing the boundaries of speed. Secondly, it provided better ground clearance, reducing the risk of foreign object damage to the engines during takeoff and landing on potentially debris-strewn wartime airfields. The engines themselves were originally Rolls-Royce Welland engines derived from Whittle's designs, but the Meteor would later be fitted with the more powerful Rolls-Royce Derwent. These engines were a marvel of engineering for their time, providing thrust levels that allowed the Meteor to achieve speeds unattainable by piston-engined fighters. The Derwent engine, in particular, was a significant improvement, offering greater thrust and reliability. The Meteor's fuel system was designed to feed these thirsty engines, with integral wing tanks and fuselage tanks providing the necessary range for combat operations. The aircraft's systems were more complex than those of its predecessors, requiring new approaches to hydraulics, electrics, and pressurization to cope with the demands of high-altitude, high-speed flight. Meanwhile, the fuselage was designed with aerodynamic efficiency in mind. Its smooth, streamlined shape minimized drag, allowing the aircraft to maximize the power output of its revolutionary engines. The cockpit was positioned high in the fuselage, providing the pilot with excellent visibility, a crucial factor in both combat and landing. While the Meteor's straight wings were not as advanced as the swept wings that would become standard on later jet fighters, they offered a compromise between the need for high-speed performance and the requirement for stability at lower speeds. The wing's thickness-to-chord ratio was carefully calculated to balance structural strength with aerodynamic efficiency. In later variants, the wingtips were redesigned to improve roll rate and overall handling. The Meteor's empennage, or tail section, featured a distinctive design with a high-mounted tailplane. This configuration was chosen to keep the horizontal stabilizers out of the turbulent air from the wing and engine exhaust, ensuring better control and stability at high speeds. The vertical stabilizer underwent several changes throughout the Meteor's development to improve directional stability, particularly at high speeds. The aircraft's primary armament consisted of 4 20mm Hispano cannons mounted in the nose. This concentration of firepower was a significant improvement over many contemporary fighters, which often had their guns spread across the wings. The nose-mounted configuration allowed for more accurate fire and easier maintenance. Later variants, such as the ground attack versions, were capable of carrying rockets and bombs under the wings, significantly expanding the Meteor's combat versatility. The testing process for the Meteor was intensive and fraught with challenges. The first prototype, powered by Rover W-2B engines, conducted ground runs in 1941, but it wasn't until March 5, 1943, that the fifth prototype made the type's first flight, using de Havilland Halford H-1 engines due to delays with the intended power plants. Early flight tests revealed several issues that needed addressing. The aircraft suffered from directional instability, requiring a redesign of the rudder. Engine reliability was another major concern, with the early jet engines prone to flameouts and rapid wear. The positioning of the engines in the wings, while beneficial in many ways, created challenges in terms of structural stress and fuel system design. As testing progressed, refinements were continuously made to the airframe and systems. The canopy was redesigned to improve visibility, and the wings were strengthened to cope with the stresses of high-speed flight. The undercarriage, initially prone to failure, was reinforced to handle the higher landing speeds of the jet aircraft. One of the most significant improvements came with the lengthening of the engine nacelles. This change, implemented on later variants, dramatically reduced drag and increased the aircraft's top speed. The introduction of the Rolls-Royce Derwent engine in place of the Welland also brought substantial performance gains. The Gloster Meteor made its operational debut with the Royal Air Force in July 1944, when 616 Squadron became the first unit to fly the revolutionary jet fighter. Its inaugural combat role was not air-to-air warfare, but rather countering the devastating V-1 flying bomb threat that was terrorizing London and southern England. The Meteor's exceptional speed made it uniquely suited for this critical task. On August 4, 1944, the Meteor scored its first victory against a V-1 when Flying Officer Dixie Dean successfully intercepted one of the pilotless bombs. This marked not only a significant moment for the Meteor, but also the first time a jet-powered aircraft had destroyed an enemy aircraft in combat. Over the course of the war, Meteors would go on to eliminate a total of 14 V-1s, demonstrating the effectiveness of jet propulsion in operational conditions. Interestingly, the Meteor's advanced technology initially proved to be a double-edged sword. Fearing that a downed aircraft might provide valuable intelligence to the enemy, British authorities initially prohibited Meteors from operating over German-held territory. This restriction was only lifted towards the end of the war, but by then the opportunity for the Meteor to engage in air-to-air combat with the Luftwaffe's Messerschmitt Me-262 had passed. As the war came to a close, the Meteor's development continued at a rapid pace. The F-3 variant, introduced in 1945, brought significant improvements, including the more powerful Derwent I engine, a sliding canopy for better visibility and increased fuel capacity. On November 7, 1945, a specially modified Meteor F-3 set a new world airspeed record of 606 miles per hour. This record was short-lived, however, as it was broken the following year by the F-4 variant, whose even more potent Derwent 5 engine and shortened wings allowed it to reach 616 miles per hour. These achievements not only underscored the capabilities of jet propulsion, but also spurred further advancements in aircraft design across the globe. Throughout the late 1940s and early 1950s, the Meteor continued to evolve. The definitive day fighter variant, the F-8, entered service in 1950. Boasting a longer fuselage, greater fuel capacity, and a standard ejection seat, the F-8 became the backbone of RAF Fighter Command. This variant also proved to be a significant export success, finding its way into the inventories of numerous air forces around the world. What's more, the Meteor's versatility led to the development of several specialized variants, each tailored for specific roles. The NF-11 Night Fighter, equipped with AIM-K-10 radar, extended the Meteor's capabilities into round-the-clock operations. The FR-9 fighter reconnaissance aircraft leveraged the Meteor's speed and high-altitude performance for vital intelligence-gathering missions. Meanwhile, the two-seat T-7 trainer variant played a crucial role in transitioning pilots from propeller-driven aircraft to the new era of jet-powered flight. While the Meteor had missed out on air-to-air combat during World War II, it would soon have the opportunity to prove itself in subsequent conflicts. The Korean War saw the Meteor in action with the Royal Australian Air Force's No. 77 Squadron. Beginning operations in July 1951, the squadron initially employed their F-8 Meteors as fighters. However, they soon found themselves outclassed by the newer Soviet MiG-15. Adapting to the situation, the Australians shifted their Meteors to the ground attack role, where they proved highly effective. Over the course of 2 years in Korea, No. 77 Squadron flew an impressive 4,836 missions. During these operations, they managed to destroy 6 MiG-15S, over 3,500 structures, and approximately 1,500 vehicles. However, this success came at a cost, with about 30 Meteors lost to enemy action, primarily due to anti-aircraft fire during their low-level ground attack missions. The Meteor would see combat again during the Suez Crisis of 1956. RAF and Israeli Air Force Meteors participated in operations, primarily focusing on ground attack and reconnaissance missions. This conflict provided valuable insights into the Meteor's strengths and limitations in modern combat scenarios, particularly when facing newer jet fighters and increasingly sophisticated ground-based air defenses. In South America, the Argentine Air Force employed Meteors during internal conflicts in the 1950s and early 1960s. These operations further demonstrated the aircraft's effectiveness in the ground attack role, even as its viability as a frontline fighter waned in the face of more advanced jet designs. Throughout its operational life, the Meteor also served as a vital testbed for new technologies. It played a crucial role in developing ejection seats, with Martin Baker extensively using Meteors to test and refine their life-saving designs. The aircraft was also used to trial various engine developments, including early experiments with reheat or afterburner technology, which would become standard on later generations of jet fighters. One of the most unusual experiments involving the Meteor was the development of the prone pilot variant. This modified F-8 featured an elongated nose section where the pilot would lie prone, a configuration thought to help pilots withstand the intense G-forces experienced during high-speed maneuvers. While this radical concept was ultimately not adopted for production aircraft, it exemplified the spirit of innovation that the Meteor helped foster in the early jet age. As the 1950s progressed, newer and more advanced fighters like the Hawker Hunter and Supermarine Swift began to enter service. The Meteor gradually transitioned out of its frontline fighter role, but its usefulness was far from over. The aircraft found new life in secondary roles, serving as a target tug for gunnery practice and even as an unmanned drone for missile testing. In these capacities, Meteors continued to serve well into the 1970s, a testament to the fundamental soundness of their design. The Gloster Meteor's legacy extends far beyond its direct combat record. As Britain's first operational jet fighter, it paved the way for a new generation of aircraft and played a crucial role in establishing the United Kingdom as a leader in jet aircraft design and production in the immediate post-war years. The lessons learned from its development and operation were invaluable in the creation of subsequent jet fighters, and its influence can be seen in later designs like the de Havilland Vampire and the Gloster Javelin. Moreover, the Meteor's impact reached beyond military aviation. The experience gained in jet engine development and high-speed flight contributed significantly to the advancement of civil jet aviation. The understanding of aerodynamics at transonic speeds gained partly through Meteor research proved crucial in the development of later passenger jets, helping to usher in the era of mass air travel. Today, the Gloster Meteor stands as a testament to British innovation during a critical period in aviation history. Numerous examples are preserved in museums around the world, including the Royal Air Force Museum in London, which houses the first prototype, DG-202/G. These preserved aircraft not only serve as static displays, but also as invaluable resources for historians and engineers studying the early days of jet aviation. A select few meteors remain airworthy, occasionally gracing the skies at air shows and serving as flying reminders of the dawn of the jet age. The Temora Aviation Museum in Australia maintains a flying Meteor F-8, allowing new generations to witness firsthand the aircraft that helped bridge the gap between the propeller and jet eras. The Gloster Meteor's journey from its genesis in the urgency of wartime development to its long and varied operational career exemplifies the rapid pace of technological advancement in 20th century aviation. Its legacy lives on not just in the aircraft that followed, but in the fundamental shift it represented in the nature of aerial warfare and aviation as a whole.